Hello, this will be a very special episode because this time I'm joined by a guest. Her name is Wiem Zine Elabidine. She's a backend Scala developer at Moya, a conference speaker, and an active open source contributor. She will tell us all about Variance, what problem it solves, and how we can use it to do bigger things like structuring our entire applications. So enjoy the video. I hope you like it. Hi, Wiem. Nice to meet you.
Hey, thanks for inviting me.
So, what is Variance?
Variance refers to the subtyping relationship between generic types.
So, what is subtyping then?
Subtyping is when a data type is related to another data type. For example, let's say ingredient could have subtypes, case object, for example, tomato, extends ingredient. And all of these, like for example, potato and chili, all of these, tomato, potato, and chili are subtypes of ingredient, and we say ingredient is a supertype of this, for example, of tomato, potato, and chili.
So, how can I use this relation between them? Could I create a variable of type ingredient and use a value of one of these subtypes as a value of that type?
Exactly, we can do this. Maybe you would like to try it. I don't know.
Yeah, let me try.
Yeah.
So I'll have like chili, which is chili.type, and this is chili, not child. And then I would have a value of type ingredient, and I would use chili. Does that work? It works. So that's the subtyping relationship between them, right?
Exactly. And if we associate like tomato as an ingredient, we can do this. We can say here tomato or any other subtypes. It's possible, but the opposite, it's not possible. We cannot.
Okay, so I cannot, for example, say that this ingredient is chili, because of course we lost the information about the type, the specific type that's inside it because of this ingredient value, right?
Exactly, yeah.
And could I say that tomato is a chili type? I can't. So no. It's a completely unrelated type. They have a common parent, but they are not related to each other in any other way.
Even they are siblings.
Yes, exactly.
They are, but the relationship is either are a child type or a parent type. As we saw here, only we can associate the subtypes for the subtypes of ingredient for a given ingredient. And in Scala, we have nothing data type, which is a subtype of all the types. Even nothing is a subtype of ingredient, tomato, integer, string, etc. And any is the supertype of all types. For example, ingredient is a subtype of any.
Okay, so I can say I'll have a value of type any, and I can put the ingredient in there.
Exactly.
Or chili, or just tomato. Yeah, or one, or a string. Okay, exactly. But if I had a nothing, I would only get this value from throwing an exception. Well, I cannot actually have a value of this, but I can only assign something if it doesn't terminate or throws an exception.
Exactly.
Okay. So now I can have like another value of, let's say, chili.type, and I can use this nothing value because it's a subtype of that. Or I can put here like Scala to 13, right? So I can use an integer here and it still works.
Exactly, because all of them are a supertype of nothing.
Okay, so I have a problem that I need to solve. Let's say that ingredient has a property. Every ingredient can be delicious or not, and this will be a Boolean. And I will implement this for every subtype of ingredient. So I'll say that I don't like tomatoes, so I'll say it's false. I kind of like potatoes, so I will say it's true. And I don't really know, but let's assume I like chili. Let's say I do. So I would like to write a function that takes a list of ingredients and only leaves the delicious ones, like
Okay.
which are delicious. And I want to return the same type. So I can easily filter it by delicious, but there's a catch to this, because let's say I call this with just chili and chili. So the result right now will be a list of ingredients, but I know that the list only contains values of chili. So I would like it to be a list of chili.type. Can I use this subtyping relationship somehow to keep this information about the types?
Yeah, we can make filter a generic function. It would be like with A, and let's say here A and A, but we
Yeah, but
cannot.
now I can't call the
Exactly.
delicious function because I don't know anything about the type A. So how would you approach this?
We can use the upper bound syntax to indicate that the A should be a subtype of ingredient, and here we can access delicious.
So this means that I still keep the same type that I put in the type parameter of the list, but I can access the property delicious inside it because we have this upper bound. So my A must be some subtype of ingredient. So if I say that this is a chili.type, then the result of the type of result would be a list of chili.type, and I don't even need to specify it here because it would be inferred. Perfect. So that's what I wanted.
In Scala, there is also lower type bound, but in this way, we cannot access the delicious anymore. And this means that A should be super type of ingredient. It should be ingredient or anything or anything that is super type of ingredient.
Right. So if I had, let's say, a new trait like food, and ingredient was extending from that food, I could say that A, when I call this, I could say, let's have another one, filter delicious with A, which is food, and that'll be a list of some ingredients. I can call it like that, right? But the implementation doesn't work. So if I wanted to keep just the ingredients and just the ones that are delicious, I could probably collect all the ingredients from that list and only keep the delicious ones. Now, this works because list is covariant, which we don't understand yet, but we will get to it. But if this was a different type, I could probably map this ingredient to an A, and all the types would match. So when I use food, I will get a list of foods. But if I said this is a list of ingredients, I would be able to say this is a list of ingredients as well. So I keep the same type because I have a generic parameter, this A, but I know that it's a super type of ingredient and not something like int because I have this lower type bound, right?
Yeah. And now when you put, for example, food, it worked because maybe it's time to show why.
How does it work? Yes, can you explain to me how it works?
Let's try an example with another type. For example, we have trait box with A. For example, if we have box of chili and then we say box of ingredient equals this box of chili, it wouldn't work. And why it worked with list here because this function will return a list, but it worked because actually list is defined as, we can see the implementation with this annotation. List is covariant in A. This plus is a variance annotation, and box here we say box is invariant in A.
So invariant is the default.
Yeah, exactly. Okay. Invariant if we say box of A, and covariant if we say box of plus of A. Contravariant if we say box of minus A. So this plus and minus call it variance annotation. And like list, if we have a covariant type, we can preserve the subtyping relationship. Like we saw with list here, we can define a list of food that contains ingredients. We will preserve the same subtyping relationship, and for contravariant, it will be the opposite. We will be able to have a box of chili that takes a box of ingredients. It's the opposite. Let's see an example.
So let me just summarize that. So if I have an A, which is a subtype of B, then a box of A is still a subtype of a box of B, right?
Exactly, yeah.
In this definition of a covariant box. But if I had a contravariant box, then if A is a subtype of B, then a box of B would be a subtype of box of A.
Exactly.
And so it's exactly the opposite.
Yeah, this is preserve the relationship, and this is like the reverse.
And so, in invariant boxes, this just the relation disappears. There's no connection between these types if we had an invariant box.
Yeah, box of A equals to box of A. Otherwise, it will not compile.
So I have a box of A, which is now invariant, and this line doesn't compile. So if I understand correctly, if I add a plus here, now it'll work.
Exactly.
Okay, so we have a covariant type box. Now let's see what the contravariant type would look like. So by my intuition, this would be something like a chef that takes a contravariant A, and the chef would have a method called cook, and it'll take an A. It can return unit for now. And if I understand correctly, I can have a chef that can cook anything, like any ingredient. And then I could assign that to a value that's a chef of chili. So a chef that can only cook values of type chili. This should work.
Exactly, yeah. And the familiar type that uses both contravariant and covariant is function. For let's take the simple one, is a function that takes only one input and returns an output. The input is contravariant and the output is covariant. Let's take an example. We want to eat ingredient, and we can call this function with chili. So this is why the input, and this is why it was accepted, because the input is contravariant.
So eat is basically a function from ingredient to nothing, right? So I could convert it to a function from ingredient to nothing, to a function value. And because, as you showed, it accepts values of type chili, that means that we could also convert this function to a function from chili to nothing. And this can be just eat or just f, doesn't really matter.
Exactly.
Right? So this relies on the fact that functions are contravariant in the type, because a function of ingredient to nothing is a subtype of a function from chili type to nothing, because of this inverted relationship between the types. But we cannot go the other way, right?
Yeah, and it is thanks. You showed in a nice way how this relationship with how the input is contravariant.
And the opposite is true for the return type, right? So I can say that it returns unit, because unit is a super type of nothing. Or I can use basically any other type. I could say it's an int, because of this nothing is a subtype of int relation.
Yeah.
Okay, so now we have a covariant type box, and we have a contravariant type, which is the chef. If I understand correctly, contravariance means that we can put values of type A in positions such as function parameters, but we cannot put them in return types. So if I have a function, like a property called value, and I put the A in the return type of it, it doesn't work. However, if I flipped the sign here, if I used a covariant type, it's the opposite. So I can only use it in return positions and not in function arguments.
Yeah, exactly. And in case if we define a type constructor with, for example, we decide to have a covariant type, it means that we want to get a value out of this. And if we have a type contravariant in A, it means that we need to have an input and use it. In case if we need, for example, let's say we have a covariant type and we need to use that type as an input, like list, for example. Here, let's say we have list, which is covariant in A, and this prepend function that has the A as an input, which is acceptable. Like we have a covariant A, but we want to add prepend an element in a list. Before we see how to solve this, why it doesn't work. Actually, the compiler prevents us to do something wrong, which, let's take, for example, a list of ingredients and let's say a list of chili. And we are clear that because list one is covariant, it accepts list one. And if we want to prepend a tomato to this list, if we were allowed to do it this way, we cannot prepend a subtype of ingredient because it considers that list one was of type chili. Here the A is chili, so it will accept only chili or its subtypes, which would be nothing. So how could we make it work? Is to say that we accept all the supertypes of A, and this way it will be considered that this is a subtype of ingredient, and L1 also.
It will work because if we write this as a function call, you can see it more clearly that the type here will be something like, basically it would be the least upper bound of tomato and chili, right? So basically ingredient.
Ingredient, exactly.
And now it will infer ingredient, and tomato is an ingredient. It will just return a list one of ingredient.
Exactly.
And this works because ingredient is a supertype of chili type, so this is the same as here.
Yeah, and also we can see that automatically the compiler could infer. And in case if you want to add string to this list, this would be the common type between all of these, which would be any. We can see. And also here we can do one.
So we can use the lower bound syntax here to specify that we can use a more wide type, such as A1, which is a supertype of A, because this is a covariant type when we want to mix a covariant type with a contravariant position. Now, if we have the opposite case, so we have an appearance of A in a return type position, so a covariant position, in a contravariant type like chef, then we need to do the opposite, right? So we should be able to say A1 is now a subtype of A, and we should be able to return A1. This probably will be impossible to implement, but there will be other cases in Scala data structures that something similar might be possible, like maybe returning a list of A1. So this is still a covariant position or something like that. I would also like to mention that these things compose. So if you have a contravariant data type in a contravariant position, then that parameter is now covariant. So if we had the function here, like merge with another chef of A, this will not work anymore because we basically have two minuses. So this parameter is in a minus position, and we have a value with a contravariant parameter. So it can only appear in the return type. But we would be able to say chef A appears in the output because it's plus and minus, which works. So even though we cannot put the chef in a parameter, we could put it in another function to do the flip again. Like if we had a unit here, then we can do this. And we can actually implement this function in several ways. Like even now, the most obvious one would be another of this. So this works. So now we have a minus here, a minus for the function parameter, and another one for the function parameter to this function here. So we have three minuses, which basically goes down to one. The two minuses cancel each other, and we are able to do this. So I understand you learned a lot of this when contributing to Zio. So how does Zio use variance to power its most important data type?
Exactly. Zio has three type parameters, and all of them has a variance annotation. It is like Zio of REA. Before I show the type annotation, you can see it as R, that if it fails, it will return an E. This is option 1. Or
Okay.
if it succeeds, it will return an A. So what do you think the variance annotation would be in Zio? By looking to this, it actually, like, you can see it like R either or of E or A. This is like two options, this or this. Yeah.
Okay, so I think because the E appears in the result, it will just have a plus, so it'll be covariant in here. The same goes for E, because it's another value that can be returned eventually by this program written in Zio. But R is something that you need to provide to call this. So it's basically a function parameter, and because of that, it will be a negative one, a contravariant parameter. Is that right?
Exactly. Yeah, exactly.
So I understand it's quite important in signatures like flatmap, right? So if I have one program, let's say it's a Zio of, I might need your help here, but let's say it's a Zio of console. It will return errors of type probable and unit. And this would be Zio console
Get.
Get, yeah. And now put string line. So this would work, right? I think it.
Yeah.
I wouldn't even need this error. Am I right?
Yeah, and the nice thing that, for example, if your program might fail with different errors, and you have, for example, a trait error, and we have many other errors, for example, internal server, and many other errors, because Zio is covariant in error type, we are able to build a program that fails with different subtypes of these errors. For example, one program will fail with internal server error, other one not found. For example, we can have a program, access and thanks, we are able to build a program. Let's do, for example, program 1, Zio of any. We don't specify any environment, but it will fail with error and succeed with unit, for example. Let's do different programs. This one would fail with internal server error. This one fails with not found. This with nothing. And then we can have a program, this here, that fails with the super type of all of these errors and combine them all together. For simplicity, we can have, this is like a flat map ignoring the previous result. It should compile. IntelliJ cannot, but this compiles because it takes the super type of the error.
Right. Maybe you can show the signature of the operator that combines these programs.
Yeah.
So it uses all the upper and lower bounds on the errors and the environment, right?
Exactly, yeah. And because the input is Zio also, and it uses flat map and ignoring the result of the left hand.
Okay. So if I'm not mistaken, I could also use my program here and combine these three programs with that as well. And this will now require an environment of any with Zio console, which is basically just console.
Exactly.
Oh, now it works.
Yeah.
But if any of these programs had something else in the environment, it would also be added to this sequence of with.
Exactly. We can try
that would be
here.
the most common type. Yeah.
Yeah, we can try clock.
Mm-hmm. Okay, so now I'll need this here in the environment of the final program. Yeah, that's pretty cool.
Yeah, and the same thing for the success result. We can have.
We can use anything here, like probably. Well, this is units, so the only super type will be any. But if let's say this program was returning int, then I could have. Let's use string because it's a built-in type. It could be like a car sequence. Probably
because there is unit.
Oh yeah, the unit is in the program here.
Maybe char, is it?
It was here in the program in the console. So let's just return something.
Because the latest result will be taken.
Yeah. Yes.
With variances in Scala helps us to know what we are doing. Sometimes it doesn't compile. We are frustrated, but then we thank compilers that we might make some mistakes even in the design. Sometimes we want to build a type and then we found out that we need it for inputs and outputs. We say, okay, let's use invariant type, and the same way for contravariant and covariant.
Yeah. Okay, so thank you for coming here. To summarize, what we learned today is we had a short recap of subtyping. We learned what lower and upper type bounds are. We also had some examples of covariant and contravariant types, and a type that's both of these things, which is function in Scala. Then we learned how to work around mixing the variance in one type. So when we had a list that was covariant, we learned how to make a parameterized argument to a function inside list. And then at the end, you showed us how to practically use variance in a more powerful type like Zio. So thank you for showing us all of that, and I look forward to seeing you here again.
Thank you for the invitation, and it was a nice session.